back, and now we're on to a whole new topic, which is pressure in liquids. So here we go. What is pressure? We feel pressure all the time, especially women who wear in high heel shoes and men who want to wear high heel shoes. But you feel pressure once the weight you have is applied on a very small area, right? However, if you wear flat shoes where you increase the area of your feet, guess what? You won't feel as much pressure. Anyway, we'll get into that. Let's not spoil things yet. So, pressure is force, thrust acting on unit area. And we say 1 meter squared or 1 square meter. And pressure, the equation for pressure is where you have force divided by area. So with this, force would have a unit of newtons, and area would have units of meters squared. And we're going to see that. So the unit of pressure is a pascal. So therefore 1 pascal is actually equivalent to Newton per square meter. Okay? Now 1 kilopascal is equal to 1,000 pascals, because remember, kilo is equal to 10 to the 3. The greater the area over which a force acts, the less pressure it's going to feel. But how is it possible that walnuts can be broken in the hand by squeezing 2 but not 1? Well, I didn't even know how to answer this question at one point, and then a student really came up with a great idea. If this is the hand and we have a walnut here, so this is a walnut, and we have a hand, do not judge my hand, okay? We have a hand here and we're trying to crush it. Well, it's not gonna crush, right? It's not gonna crush because the surface area is really broad up here and down here and all around here. So the force exerted on that surface area, the area is just too large, right? However, if you have 2 walnuts inside your hand, right? Now you've created a very small area between the 2, right? And the same force you were applying in the first scenario is now being applied in this scenario right here, right? And let me draw some more fingers right here. And so because now the area here is smaller between the 2 walnuts, but the force is the same, so let's draw the force. So let's say a force of 10 newtons is applied to each section. But however, the area here, this area that we're pressing on, is much larger than this area between the 2. And so when you crunch them together, the pressure is now greater. So pressure is greater here than here, right? And so in this case, pressure is greater because the force, because the force is the same, but area is small, right? However, in this case, pressure is smaller because the force is the same, but the area is large. So long as area is large, right, pressure will be small. So long as area is small, pressure will be large. If the force is the same, if the force applied is the same. So why do you think that wearing skis prevent you from sinking into the snow? Now, I always tell children, let's just draw this scenario. And skis, so I'm guessing the thing. So basically, if you here and you put on boots, you're gonna sink, right? You're gonna sink. you're going to sink simply because your force being applied is on this area here, your feet. Okay? And so now you have your force, this is you, and this is the area. So your force and the area is small, the area of your feet small collectively, and then of course if you have force, small area, just like the last one, what's going to happen, you're going to have big pressure, so you're going to be able to penetrate the snow, right? However, if it's the same you, and now you put on skis, I forget how skis are, right? So you have these skis, and now that's the ski right there, and you have your foot on the other ski, you have the other ski, right? Now you have increased your area, the area that your foot once was, you have increased the area, right? And let me try to draw this again because now I have an idea how it should look. Okay, so let's do this here, and so you have your feet here, here, and then you have your feet here, here, and you put the skis on, move the skis kind of along, and then the second foot would also have skis. So now you've now increased your area, the force is the same, but the area has increased somewhat. So you're not going to sink into the snow. So therefore pressure will be minimal, force being the same, however area would be much more. Right? So that's pretty much how I would explain it. So I hope you understand that. Pressure in liquids increase with depth. Pressure at one depth acts equally in all directions. So if you look at it from here, of course the force applied here will be less than the force applied here, because at this point it's much less water acting at this point, right? Much less. However, as more water gradually increases coming down here, you feel a greater force, right? And therefore the pressure would be greater here, and it's the same thing here. Pressure is greatest, right? The force is great, right? And then in this case dealing with liquids, so I can't even use this equation, but just now let me not use that equation because it's a whole different equation for pressure in liquids. For pressure in liquids, we use the equation pressure equals to the density of the water times the gravity acting on the water times the height of the water. So height is height would cause an increase in pressure, right? Also density plays an important role in pressure as well, and gravity. So therefore if you increase the height, well, gravity is constant because we know that would be 10 newtons per kilogram, and well, we would know that pressure is specific to the solution, right? Height therefore would therefore be a very important role in how much pressure will be felt at any given point. Okay, so let's say that let's just imagine that the density of this solution is 1. Let's just imagine it's water, so I'm guessing 1000 kilograms per meter cube, right? And so if we say 1000 kilograms per meter cube times 10 newtons per kilogram times the height. Let's just say the height here is a meter. This is a meter. Then we're going to end up with 10,000, right? However, if this is 0.2 meters, we're just calling numbers. It's not going to be 10,000. So if you say this is 1,000 kilograms per meter cube times the 10, which we know is constant, times is constant in this case with the density as well, because we're dealing with the same liquid. So if we have that times 0.2, then we're going to have what? 0.2 meters. We're going to have 2,000. So this in this case would be much less. So this would be 2,000 right here. 2,000 Newton meters squared. And then this one will be 10,000 Newton meters squared. So definitely height plays an important role here. It determines the amount of pressure felt. So therefore you will definitely feel more pressure at the bottom than at the top. Okay? And a lot of divers experience this. That's why they have to gradually descend into water when they're swimming. Otherwise the eardrum is going to pop from all the pressure. Remember, if you're up here and you're swimming down, you're a diver going down, right? You're a diver going down. You have your little goggles on and your little tank or whatever, and you're going. Remember, the pressure of the water is acting on you, and it's ever increasing the more you descend, right? So that's a lot of pressure. And don't forget that the atmospheric pressure is also going to be pressing on top of you. So you have to be careful when you are actually diving. Now, pressure acts in all directions equally. So if you punch a hole in a plastic bag around in a circle, the water will come out at the same pressure, same intensity. So liquid finds its own level, and pressure depends on density, because yes, if I were to say this was not water and we're now dealing with mercury, right? Mercury is liquid metal at room temperature, and the density will be way more. I don't even remember the number for it, but it's not 1,000, it's way more. Your answers will be much more, right? So pressure is definitely dependent on the density of the solution, the liquid you're dealing with, and it's dependent on the height of the liquid. Now, a town's water supply often comes from reservoirs on high ground. And the question is here is asking why. And of course we know the higher up you go, the more pressure something would experience, remember? So height is important. Gravity is going to act on that. And also we need to talk about the density of water. So the higher up something goes, the more pressure will be felt. And so the intensity and the flow would be faster in these pipes, right? And so once we have a fast, steady flow coming from the top here, then we wouldn't have to worry about finding pumps to pump the water down and stuff. However, when we want to store that water coming from the reservoir into a water tower, we do have to install a pump to get it up there. And then when we store it up there in smaller villages, and again you need a pump to pump that water into the houses. But using natural flow saves a lot of money in terms of installing pumps everywhere. We just need the pumps to when it comes to storage. And then again, in some houses the water is stored high up in a tank up there, so that at least water pressure will be favorable when you're washing your skin. So the water flows from the reservoir via pipes to any tap or storage tank that is below the level of water in the reservoir. The lower the place supplied, the greater the pressure felt, because again, height height. Pressure is dependent on height. The size of pressure is dependent on the height. In very tall buildings, it may be necessary for us to pump the water to a large tank on the roof, and that's simply because if you only depend on natural flow, right, coming from a reservoir, it will not, that intensity will not be able to carry the water to the top of very tall buildings. At some point, it's going to level off and just stop. It's not enough to push that water up. So we pump the water up to the top in a tank, because people at the top in the penthouse and in wherever at the top, the special places in hotels and tall buildings, need to experience good pressure. Because could you imagine if there is no pump and if there is no holding tank, the pressure from the shower head will be a drizzle. Who wants to bathe in a drizzle when you could enjoy full force, right? Sometimes you bathe in trickle water and you don't even feel like you had a bath, right? So basically, you have these large tanks that on the top of the roof so that you could achieve high intensity or pressurized water coming out of the nozzle in baths or out of taps. So reservoirs for large supply of hydroelectric power stations are often made in mountainous regions by building a dam at one end of the valley. Why must a dam, when built, have much thicker base, right? So in larger countries, they would have these huge dams to supply, of course, the million people that they need to supply, right? And so because of this control of water, they have to build a wall that could withstand the pressure that builds up as you go down. It's so much water that the thickness of the wall must be considered at the bottom to combat or to override the intensity of the pressure down here. Because if the wall is not thick down here, could you imagine what's going to happen? A thin, normal size wall running from top to bottom where pressure increases gradually as you go down. And this pressure is going to act or push on this wall, and it's going to cause the wall to buckle, and it will cause a flood, right? And so this flood now would affect the, if you have a dam up here, you have the water, and the town is always lower than the dam because you really want pressure, natural flow pressure. Now this dam breaks, and the next thing you know, we flood out the whole town, kill people. It's a disaster, right? What are some forces acting on the wall of the dam? So force could be push, a very strong push on this wall right here. So we're dealing with hydraulic machines now. So liquids are almost incompressible. What do you think this means? That means you can't squish the water. You can't squish it without it conforming. It would find a way to get out of your hand. However, they are able to pass on any pressure applied to them, and use of this fact is applied to how hydraulic machines work today. Suppose a downwards force of 1 Newton acts on a piston A of area 1/100 meters squared. What is the pressure transmitted through the liquid if pressure is equal to force over area? So this is our force and this is our area. So if you say 1 Newton divided by 1 over 100 meters squared, what we end up with is 1 times 100. Well, 1 Newton times 100 meters squared, right? And we end up with 100 Newton meters squared. Pretty sure I did that correct. Okay, so that's the pressure, and that'll be 100 pascals. So this pressure acts on piston B of area. So basically we have this small little area right here, and this is piston A, and we have a 1 Newton acting down, and then it's filled with some kind of water onto a larger area. This is B right here. And so they're saying this pressure acts, so we found out that the pressure that's acting here is 100 newtons per meter squared, and the area of this is a half a meter squared. Half a meter squared. So what is the total upwards force or thrust on B if force is equal to pressure times area? So we have the pressure from up here, the pressure traveled through the liquid as said before. So we can say 100 newtons per meter squared times half a meter squared. And that will give us 50 newtons. So that would be the force that this would feel right here. 50 newtons, right? So therefore a force of 1 Newton applied on piston A thus produces a force of 50 newtons on piston B. Could you imagine? You only had to apply 1 Newton to get this large force being applied to the next piston there. So that's why hydraulic machines are so great, because then you've used hydraulic machines if you've driven, right? And it says then that you, being the person operating the hydraulic machine, would only have to exert a very small force to lift a very heavy object if you had to do so. And you could see this in hydraulic jacks, where people, this kind of jack especially, you only need to use your hand, and it looks so effortless, and it would lift an entire car. Could you imagine? A really big car. Hydraulic forklift trucks and hydraulic car brakes also use this very same method. So the force you apply is so minuscule that you don't even feel it. But however, it achieves something grandiose, meaning that, wow, I could use this small little thing. It's not too small, but it can be manipulated it could be easily manipulated then, right? You could store it in the back of your car if you wanted to, and it could lift up a whole car instead of the old time ones where you had to crank up with your hand. I don't know if anybody here really had to use that. The old time one, you had to crank up and you used to feel it. You'd be like, oh. That's a really good one, a hydraulic car jack right there. Now the pressure in liquids, we don't use pressure equal to force over area when it comes to liquids on a whole. We use pressure equal to density times gravity times height. Okay? And this pressure acts equally in all directions at depth h. And it depends only on the height of the density, on height and density. Right? Yes, it depends only on height and density, because you know that gravity is constant. So its value will be in pascals if height is in meters, and like I say, you always have to pay special attention to your units, and density is in kilograms per cubic meter. The expression above also applies to gases, because gases are also viewed as liquids. Okay? So, well, as fluids. So we call liquids and gases fluids. Within a fluid, difference in pressure between points separated by a depth in change of height can be written as change in pressure is equal to rho g change in height. The symbol delta means difference in. So the figure below, the figure on this side shows a fish at a depth of 40 meters. So fish is at 40 meters right here. In a lake where the density of the water is 1,000 kilograms. Determine the pressure due to the water. Determine the pressure due to the water on the fish, right? So they want you to calculate the pressure that the fish feels from the water. So we would say pressure of the water will be equal to, rho GH. Right, so it's equal to rho GH. And we know that we're dealing with 1,000 kg per meter cube times 10 newtons per kilogram times 40 meters. And we have all the units that we require. And since we have 3, 4, 5 zeros, so 1, 2, 3, 4, 5, and of course the 4 times the 1, so 400,000, 1, 2, 3, 4, 5 newtons per meter squared, and that's equal to 400 kilopascals, right? Now we said gravitational field strength 10, and then it says the total pressure on the fish if the atmospheric pressure is 10 to the 5 pascals. So 1 times 10 will give you 10 to the 5. So all we have to do is say total pressure, so P total will be equal to 400,000 pascals plus 1, 2, 3, 4, 5 pascals, and that will give us 2, 3, 4, 5, 500,000 pascals, which is actually 500 kilopascals, right? And I just did the calculations so that you could see it in real time, and that's exactly what we have down here, right? Good. So I hope you were doing the calculations with me. So take a look at the question and try to answer it. It says, answer the following questions where atmospheric pressure is equal to 10 to the 5 pascals and gravity is taken at 10 newtons per kilogram. So it says a girl in setter heel is more likely to damage a wooden floor than an elephant. Why? Well, an elephant, right, has broad feet. Very broad feet. It might be heavy, but its weight is properly distributed across its very broad feet. And so, because of this, pressure will be much less if the force is large, but the area is large. Right? The force felt over the area wouldn't give us a very high pressure. Right? However, a woman, I mean the comparison is not too good, but if you look at a person, because some men wear heels, and all her force is on something like this, her heels, but then all her force is on just an area that looks like this, because this is the imprint of the bottom of some heels, right? So because remember the heel is like this, right? So this part is that, and this part is the heel, right? So her force is exerted on a very small area. So therefore, oh, I made a mistake. Oh my God. So her force, small area, large pressure. Right? Oh, I didn't make a mistake. Good to go. Let me make sure. Force is a larger area, so the pressure will be felt less. A woman. So then Because of that, if the floor is not cured or if it's weak wood or anything like that, she can make indentations in the wood. So it says now, what is the pressure on a surface when a force of 50 newtons acts on an area? So we're dealing with some solids right about now, and we know the force is 50, and then we have these areas here. So if we know the pressure equal to force over area. So for A, we're going to have 50 newtons over 2 meters squared. B, we're going to have 50 newtons over 100 meters squared. And C, you're going to have 50 newtons over half a meter squared. And this will give us 25 newtons per meter squared. This one will give us 0.5 newtons per meter squared. And this one will give us 100 newtons per meter squared. Right? So that will be the pressure there. And if you look at it, the one with the highest area, note that all the forces are the same. The one with the highest area exerted the least pressure, and the one with the least area exerted the highest pressure. See? So a pressure of 10 pascals acts on an area of 3 meters squared. What is the force acting on the area? So if we know pressure is equal to force over area, we could transpose by multiplying both sides by area. And then now we have force is equal to pressure times area. And we see here that the pressure is 10 newtons per meter squared. And the area is 3 meters squared. So that will give us 30 newtons. That's the force. Now, moving on, a block of concrete weighs 900 newtons and its base is a square of size 3 meters. What pressure does the block exert on the ground? Now, it says the block has a base of 3 meters. So we have to find the area of this square block. And so the area will be equal to length times width. And that will give us 3 meters by 3 meters, which is actually equal to 9 meters squared, right? So notice that what is the pressure? I mean that pressure is equal to force over area. So if the force is 900 newtons, then you would divide by the 9 meters squared. And that should give us 100 newtons per meter squared. So I hope you got that. And that's how much pressure is exerted on the ground. Now it says in a hydraulic press, a force of 20 newtons is applied to a piston of area 0.2 meters squared. The area of the other piston is 2 meters squared. What is the pressure transmitted through the liquid? So we have force right here and we have area. So we know that the pressure would be force over area equals to 20 newtons over 0.2 meters squared. We could do this as 200 newtons over 2 to get that point off, and then we end up with 100 newtons per meter squared, right? Sorry, yes, 100 newtons per meter, which actually translates to 100 pascals. So the force on the other piston. So now we're going to use this pressure, where the pressure is equal to 100 pascals. And then we want to find force. And we have the area. So the area of the other one is 2 meters squared. So we know that if P is equal to F over A, then F is equal to P times A. So F therefore would say 100 newtons per meter squared times 2 meters squared will be equal to 200 newtons. So force of 20 newtons could produce a force of 200 newtons on the next side. Could you imagine that? That's amazing. So what is the pressure 100 meters below the surface of seawater of density 1150 kilograms per cubic meter with a gravity of 10 newtons per meter squared? In this case, I put the wrong thing. It should be per kilogram, right? So it's we're dealing with liquid. So you know we're going to say pressure is equal to rho GH. That little thing stands for rho, which is density. So the density of the water is 1150 kilograms per meter cubed. The gravity is 10 newtons per kilogram, and the height is 100 meters. And the good thing is that we have all the units that we want, and we left back with newtons per squared meter. And now if you multiply this, you just add the zeros across the board. 11, 5, 0, and we add 3 more zeros, right? So we get 1,150,000 newtons per meter squared, and that we would get 1150 kilopascals. And that's the answer for that question.